I'm Pat Dugas. This screencast is about roots and zeros of polynomials, using the fundamental theorem of algebra and Descartes' rules of signs and the complex conjugate theorems. So let's put it all together. The ideas, the concepts of zeros, factors, roots, and intercepts. So if I have a polynomial function, and I say that some number c is a zero of that polynomial, that is the equivalent to saying that that number c is a root or a solution of the equation the polynomial equals 0. That is also the same as saying that x minus c, if x is our variable, is a factor of the polynomial because it is a 0 and it is a root or solution. And finally, that also tells us that c comma 0 is an x-intercept. So all these terms are related to each other. The factor, the root, the solution, the 0. They're all tied together. And so here's an example of a polynomial function. And we learned that the zeros are at -3, -2, 1, and 2. Okay? That also means that's where the x-intercepts occur. And those are the roots of the polynomial equation when we set it equal to 0. And finally, that also tells us that x plus 3, x plus 2, x minus 1, and x minus 2 are all factors of this polynomial. In fact, if we multiplied them all together in a massive distribution and distributed them out, we would get exactly that polynomial. And so each of those points is also an x-intercept as well. So that brings us to the fundamental theorem of algebra, and that is every polynomial with a degree greater than 0 is going to have at least one root in the complex number system. Now the exception is a polynomial with a degree of 0, which could be a horizontal, which is a horizontal line. May not have that, but any other polynomial does. Any kind of polynomial we can imagine has at least one root in the set of complex numbers. Now it may never hit the x-axis. I'm going to draw one that doesn't ever hit the x-axis. Okay, it could be something like this. That is going to still have complex number or imaginary roots. The one on the left has certainly real roots and possibly some imaginary ones. The one on the right here has complex imaginary. And the corollary to that fundamental theorem of algebra is that a polynomial of degree n has exactly n roots in the complex number system. It is a combination of real and imaginary roots. For example, this third degree equation will have 3 roots, some combination of real and imaginary. This fourth degree polynomial, 4 roots. This fifth degree polynomial, 5 roots. So let's look at an equation and determine the numbers and types of roots. So I've got x squared, we've got x squared plus 2x minus 4 equals 0. How many roots does it have and what are their types? Well, we know by the fundamental theorem of algebra that it has 2 complex roots. Whether they're real or imaginary, it has 2 complex roots by the fundamental theorem of algebra. Now, whether they're real or imaginary is going to be determined by factoring. So if we take that polynomial, which is a quadratic, and we factor it, it actually factors to x plus 8 times x minus 6. And so using the zero product property, either x plus 8 is equal to 0 or x minus 6 is equal to 0, which leads us to 2 roots at x equals -8 and x equals 6. So this equation has 2 real roots. We knew it had 2 total complex roots. Turns out they're both real. It has no imaginary roots. Let's look at another one. Y to the 4th minus 256x equals 0. How many roots is it? What are their types? The fundamental theorem of algebra says there are 4 complex roots. They are some combination of real and imaginary roots. Let's go ahead and solve it. So a couple of ways to solve this. One way is to go ahead and factor it. And so when we factor it, it actually becomes a y to the 4th is a perfect square of y squared. And so this is a difference of perfect squares. 256 is a perfect square of 16. And so we get y squared plus 16 and y squared minus 16. We can actually factor that further. The y squared minus 16 can itself be factored as a difference of squares. y squared and 4. So this becomes y plus 4 times y minus 4. We cannot factor y squared plus 16. It is there is no pattern for the sum of perfect squares. And so that leads us, using the zero product property, to eventually to 4 solutions. So on the real side, either y plus 4 is 0 or y minus 4 is equal to 0, which leads us to these 2 real solutions. So these are our real solutions, negative 4 and positive 4. We have to go a step further with y squared equals negative 16. When we take the square root of both sides, and we remember our properties of imaginary numbers, the square root of negative 16 is going to be plus or minus 4 times I. So it turns out these 2 roots, 4i and negative 4i, are our imaginary roots. And imaginary roots have to come in pairs. So this equation has 2 real roots at negative 4, x equals negative 4 and 4, and 2 imaginary roots, 4i and negative 4i in the complex number system. But it still has that total of 4 roots because of the fundamental theorem of algebra. So let's look at René Descartes, a French mathematician of great fame. And René Descartes developed something called the rule of signs, which is if I have a polynomial and I have it in descending order and it has real coefficients, then the number of positive real zeros is the same as the number of sign changes. And by sign, S-I-G-N changes, we're talking about if I go from positive to negative or negative to positive. Okay, that's what a sign change occurs as we go from left to right. So the number of positive zeros is going to be the same as this number of sign changes, or less than that by an even number. In other words, let's say we got 6 sign changes. Well, it could be either 6 or 4 or 2 or 0. It is possible to be 0. In a similar way, Descartes' rule of signs says the number of negative real zeros is a result of the sign changes in p of negative x. So everywhere you see an x, you input a negative x, you count the sign changes, you look for how many there are, and the number of negative real zeros is equal to that number or some even number less than that, all the way down to 0. And I know that sounds really complicated. We're going to do some examples. So finding the number of positive and negative real zeros, and again, Descartes' rule of signs is only for positive and negative real zeros. So we've got this function, negative x to the 6th plus 4x to the 3rd minus 2x squared minus x minus 1. We want to find the zeros, the real zeros using Descartes. First of all, using the fundamental theorem of algebra, since it's a 6th degree equation, we know there are a total of 6 complex roots to this. So we're going to use the rule of signs to determine the number and type of real roots. And that can also help us figure out how many imaginary are, because the total of real plus imaginary has got to be equal to that number 6. So let's look at the positive side of things. Okay, so if we just look at the regular polynomial here and we count the sign changes, we go from negative to positive here, so that's a sign change. We go from positive to negative here, that's another sign change. Then we go from negative to negative, and then negative to negative. Those are not sign changes. So 2 sign changes on the positive mean that we either have 2 or 0 positive real zeros in this polynomial. Looking at the negative, and this is where it gets a little bit more complicated. Now what we're going to do is we're going to put in a negative x to look at the negative side of things. So when we simplify this, the negative x to the 6th stays the same. When we put a negative x into this term, however, the sign changes from 4 to negative 4. Similarly, putting it in here doesn't change the sign from its original, but putting in a negative x to the 1st definitely changes the sign. So our new polynomial with negative x in it is this one right here. And so if we're looking at sign changes from 1st to 2nd term, no sign change, negative to negative. Then we have negative to negative again, no sign change. However, when we go negative, when we go from this term to this term, we go from negative to positive. So there's 1 negative real root. And then it changes again from positive to negative. So we have another one. Total, either 2 or possibly 0 negative real zeros. So now we put it all together with the 6 that we know we have total in the complex system. So from Descartes' rule of signs, we know we have 2 or 0 positive reals, zeros, and we know we have 2 or 0 negative real zeros. What that leaves is the remainder to be imaginary zeros, and depending on how many positive or negative real zeros there are, it's either 6, 4, or 2 imaginary zeros in this case. So making a table of all the possibilities, and there are basically 4, helps. So if we had 2 positive real zeros and 2 negative real zeros, that would make 2 imaginary zeros for a total of 6. We're adding up the totals along the row. Another possibility is that we have 0 positive and 2 negative. That leaves 4 imaginary. The imaginary is kind of the remainder. Then if we have 2 positive and 0 negative, then we would have 4 imaginary zeros for the total of 6. And then we could possibly have no positive or negative at all, which would leave 6 imaginary zeros. And so these are the 4 possibilities for this particular polynomial. Now, one interesting note, if we have a complex root, it always comes in pairs. And this is related to the quadratic formula, but it kind of expands it. This is called the complex conjugates theorem. So any polynomial function with real coefficients, if a plus bi is one of the 0, and that's, if you'll recall, is a complex number, then a minus bi must also be a 0. And the reverse of that is also true. So if you get one of these as a 0, the other one, its conjugate, has to be a 0 as well. So for example, if I'm told that 3 plus 4i is a 0 of this polynomial function, then I know by the complex conjugates theorem that 3 minus 4i must also be a 0. So complex roots always come in pairs. So in this screencast, we looked at using the fundamental theorem of algebra and Descartes' rule of signs to determine the number and type of roots to a polynomial equation, and also finding the zeros of a polynomial function.